So again, you'll see there is this recording from a previous semester, spring 2023. I've actually I've added a few things that I think will be more meaningful. So we'll see. I'll kind of try to focus on those. Okay, so as you see, we're actually in chapter 10, which is Introduction to the Derivative. And today's where we're really going to do that. So we've talked for 2 sections about something called the limit, getting close to something. You're going to see why we need that concept. We don't really use it in our technical part, but we need to know that that concept of limit can work, and you'll see that today. Okay, so average rate of change. What is the average rate of change? It's a slope of a linear equation, a straight line. It could be, again, let's put it to something we're familiar with maybe, if you're driving or walking, whatever, it's your speed. The average, what's changing is your distance over time. So when you're driving 55 miles an hour, that's your rate of change. And if you drive from here and you drive for 2 hours and you average 55 miles an hour, does that mean you were always going 55 miles an hour? No, you may have been going faster or slower, but the average, if you were to take your time, the 2 hours and your distance and divide it, you'd get 55. So that's average rate. Doesn't mean that's exactly what happened. If you were able to drive exactly 55 miles an hour for 2 hours, then your average rate and your actual rate are the same. But we're going to see in most of what we do, that doesn't happen. So when we think of average rate of change, what we need a starting point and an ending point. Or let's throw out those, we need 2 points, and it's the rate of change between those two. It's the slope. It's really just the formula y2 minus y1 over x. So it's the change in the y's divided by the changes of the x's, right? So we've got an example here. It's just some data. Year 2008 is represented as 8, 2009, and so forth. And these are the values of the S&P 500 index, stock index. So higher value means is higher. So we can see it just following this trend between the year 8 and 9, 2008 and 9, it dropped, went back up, so forth. And so then the question is, the types of question we'll have you be doing in the homework is we'll give you data like this, and we'll ask you what is the average rate of change over various periods. So we've got 2 endpoints here. The first question is going from year 10, from year 10 to year 14. And so what we do is we take the 10 as an ordered pair, and we take year 14 as an ordered pair, and we take its slope, right? We take y2 minus y1 over x2 minus x1. So that's 1800 minus 1150. And then in the denominator, we're going to subtract 14 minus 10. So those are the x values, right? And so to the bottom, it's easier. There's 4 in the denominator. 1800 minus 1150 is going to be 650. And 4 goes into 650 how many times? 162.5. And for the units on this, notice the x values are years, the y values are points. And so the y is in the top, the x is in the bottom, so that's points per year. Okay? So the units are points per year. And in the homework they ask you for the units as well as while you're getting the average rate of change. So what's changing? The points are changing over time. That's what's happening. So this is saying while it didn't happen necessarily every year, right? We go from 10, it actually went up. 13, it went up a little. See, I can see it only went up. Actually, it went up, and then it stayed the same this time, and then it went up another 100, and then it jumped up here. But what it's saying is, on average, it went up 162.5 per year. Again, it didn't actually happen that way. There was more change at the end than at the beginning, but on average, it was like every year it went up 162.5 points. Okay, so that's the average rate of change. And again, we could do it for each of these 8 to 10. You would take 8 and 10, and you'd find their slope. But I'm going to not work through those because it's actually here in the PowerPoint. Yes.
Configure 162.5 to a percentage.
Percent change. We could talk about that, but we don't have to do that in here. So percent change would be this. We would take these values and then we divide by 1800. So that would be the total change. But then if we're going to do the percent change, we've also got to talk about, do we want it over the 4 years or do we want it up per year? And so those are a little more complicated than we're going to need to do for this part. Okay, so all we're going to get is the average rate of change. So it's the y's, subtracting the y's, divided by the x's subtracted. Okay. And we get a rate that's based on the units that we have. So we're not going to, I think we do talk about percentages later when we get to exponentials, but for this one we're not going to get into percentages. Okay. So again, you could do it for the other two, but what I'm going to show you is that I left this in. This is the textbook going through, but I felt it would, if I just kind of show the slides, it feels artificial. So, but the slides are there to kind of look through. They're subtracting, and they did this. They took the output values. They got 650 like we did, and then that it happened over 4 years. 14 minus 10 is the 4, 162.5. So that's the average rate of change. Change in dollars over change in time. So then they, again, just kind of giving some more. This is what I just sort of jumped to this. This is the output at 14. This is the output at 10. So here's another way to do it using sort of the slope formula. This is how we did it. Okay, so the slides will show you multiple ways to go through those. So use those as your resources. Interpreting the result. Again, we talked about this. What it means is that on average, over those 4 years, on average, the S&P went up 162.5 points each year. Didn't happen, actually. 1 year it didn't change at all, and another year it changed by more. But on average, that was what was happening. And we use this a lot of times because in business, maybe we're missing the data in the middle. We just have these two ends, and we don't really know what happened. Somebody wasn't keeping records. But we can say, we started here, we ended here. This was what happened on average. But be careful, sometimes the average is not, you can tell the police, I averaged 55 miles an hour. Well, yeah, there was that instance I was going 210, but hey, so average doesn't always cut it, But again, some more examples. And again, you're going to see as you go through this one, the technical side of what you're going to do is really just from algebra. You're going to pull out the 2 points, you're going to ignore all the other points, and you're just going to find the average rate between those two. Okay. What I want to do is again, they go through and they do it for each of those. Now what they ask us to do is to graph the values in the table and how's the change reflected in the graph. So I've set this up with a Desmos graph, so we'll go to that and we'll start. Let's see. Okay, so I went ahead and put the data because that's kind of boring. So if you click on the plus sign, you can have a table, fill it in, and then I resized it so we can see all the data. So we see it started at 1400, it went down, it went up, and then it's leveled off here. What we can do, I guess I got rid of that, is to see the result. Let's see, we were going from 10 to 14, right? So 10 was 10 was 1150. Oh, I suppose I could have just looked down there. And then 14 was 1800. Let me kind of do this. This feature here, I can actually put in a line. So we're connecting these as if there's a line, so that's kind of a trend line. And I can do the same thing up here. Let's make this red, and let's put that line in. And so that's what we get to see is the average rate of change between 2010 to 2014 is that red line. So that's sort of that's over the 4 years. That's what happened on average, but we see that what actually happened was different. Okay, but this is what we call a secant line. We're going to take a look. If we've got a graph, if we're taking the slope between any 2 points, notice it doesn't really go so. It actually almost goes. This line sort of seems to have the same slope here. So at least for these 2 years, this trend kept going. Again, it broke off, but we call this a secant line, and we're going to do this with graphs as well. Okay. And that's where we move to pretty quick. And again, we could do this with any 2 points that we were given. So I think they also went like, we wanted to see what happened between the year 8, which was 1400, and year 14. So from beginning to end, this is what happened on average. Again, if you're an investor, you weren't too happy in this year, but if you held on, overall it was okay. But you had some maybe sleepless nights there for a while, and it took you a while to get up there. But that's your average. So that's what we're going to talk with calculus. That's what the derivative is. It's the derivative is not the average rate of change. We're going to take a way of looking. We're going to use bring in the limit, and we're going to be able to find a way to get the instantaneous rate of change. But this is where we have to start, right? What do we need to get a slope? 2 points. You have to have 2 points. For a derivative, we're going to get the slope at a point. So anyway, you can pull up, you have access to this, so if you want to play with this a little bit, that's fine. You might want to play with some of the other ones I'm going to show you. So this is what the textbook shows. Again, this is the plot that I showed you. You could do it as a bar graph, but you can see it's changing at various rates. And then they go through, and again, I'll let you go through this, but they go through the calculations like we did, and they show that from year 8 to year 10, those are the 2 points. If they were to connect them with the line, that's the average rate of change. It's a decrease. Again, if you're an investor, you still don't like this very much. You want to maybe get some of these others, but that's the average what happened over those 2 year period. You missed the good news. I mean, if you made it through this time, you're actually recovering some, right? But if you just look at these 2 years, all you see is an average negative change. Okay. Okay. So the formulas, and again, what we're going to see is it's just what we talked about, is y2 minus y1 over x2 minus x1, or with function notation, what they're going to do, it's the output values, right? These are your y's. So they give you 2 points, A and B. A is the starting point, B is the ending point. So however you want to do it, but it's the change in the output values divided by the change in the input values, right? And it's really helpful because in the tables that they're going to give you or whatever, they will generally have what the units are. And remember, whatever the y value units are, that's in the numerator. Whatever the x value units are, that's the denominator. That's the per. So, if you're traveling, that's miles per hour. If you're investing, that's dollars per year or points per year, something like that. But that helps you relate to what's going on. Okay, so just again, this is strictly from algebra. But what I want to do is let's see, how much time do we have? We got about 15. Good, because I want to get 5 or 10 minutes to kind of wrap it up. I want to show you where we're going with the calculus, because this is all algebra to this point. Would you agree with me on that? Pretty much algebra stuff. This is where we're starting to introduce calculus. Okay, so we've got now, instead of just a table of values and some, I mean, a lot of times in business that's where we're at, but we've actually got a function, a curve, and this is what we're introducing something, they're calling it the secant line. I'm not really sure, secant is a word from Greek, it's from geometry. I really don't know what it means, but it's taking 2 points on a graph and connecting them. That's a secant line. We're going to compare that to a tangent line, which is a line that goes through one of the points. So that's the goal we're trying to get towards, is the tangent line. And that one, most of us have some, going off on a tangent is, yeah, you go off this way and the graph went off that way. But we start with the secant line because that's all the math we have is algebra. We need 2 points. So with algebra, all we can do is get a secant line. What we're going to do with, and again, we could go through and find the slope of that secant line. What you do is you find the 2 output values, subtract them, the 2 input values, subtract them. So it's really the same process. We're just doing the slope formula, and the units, billion of dollars per year, come directly from the units that were given for the setup, right? This is telling us that it's tracking things in years, so the input is years, the output is in billions of dollars. Okay, so the units on our slope are going to be $1 billion per year. Okay. Now we're going to look at another example, and this one's going to be a little bit more visual. So here's a function that we're told fits the spot market price of gold on an ounce of gold on a particular day. And so the time is they're tracking the cost of gold from 7:30 in the morning till 10:30 in the morning. Okay, so that's what we've got. They show us the graph of what's going on. So from between 7.5 to 10.5, so 7:30 to 10:30 in the morning, this is what happened to the price of gold. And it didn't actually, maybe it looks something more like this, but a smooth curve, they got a graph a function that fit the data. Okay, a lot of times we'll do this. It's not the exact data, but it's actually easier to work with now. We can model things. Okay. So we want to be able to look at what is the average rate of change at various times. So I'm going to do that using Desmos, mostly just to show you what's happening. So if we wanted to calculate this, we've got 8 and 9.5, and I think they do go through and calculate it. You would plug that into the function. You'd get 2 y values, right? Subtract those, and then divide by 1.5, because you subtract these, you get 1.5, and that would give you the average rate of change over that hour and a half. What I'm going to do is I want to show you graphically what's going on. Again, if you click on that, this is the graph. I've got a little bit more, but it's pretty much, it is the same graph as you can see up here. I've got 2 points on here. I've got A, and I've got B, and I've got this set up with sliders. And again, this is something you have access to, so you can kind of play with this. You can see that it's going to calculate the slope for us. It's taking the output value at B minus the output value at A, divided by B minus A. And you can see, let's see, if I take A and move it to 8 o'clock, because that's what they wanted, and then I take B and I move it to 9.5, and you could do it this way too oops, there we go. And I see that the slope is 2.5. We're going to look in the PowerPoint, will do those calculations and they come up with the same thing. What I did though is I used the point slope formula for the line so that I could also show the secant line here. Okay, so it's the average rate of change. This is the whole graph of what's happening from 7:30 to 10:30. I went out a little bit more, but I can get that average rate of change. The reason I want to show you this is I can move both those points. So what we're working with on calculus, this is kind of where we're going next, is we're going to use limits So we will find the slope as these 2 points become 1 point. And I want to show you what happens when those 2 points become 1 point. What happens to the slope? Any ideas? It looks fine. It's still got slope there, right? But when they become 1 point, whoops, the slope's undefined. Why is that? At the same point, you've got 0 over 0, right? The line disappears. You don't see. But what we're going to do is we're going to use the idea of limit. If we snuck up on this, there's actually a tangent line here. There's not a secant line anymore because there's only 1 point, but there will be a tangent line. We'll get that going. But what we can do is kind of think of limits. If I maybe back this one down just a notch, so I've got it at 9.48. Notice my slope is 9.99. If I go maybe the other side, switch them, I got 10.05, 10.2. So I go to one side, I've got a little bit, I'm getting closer to 10. I'm getting up there. If I go to the other side, I'm a little bit bigger than 10. So what do you think that slope would be at that point? Maybe 10. 10. Because of limits. Okay, so that's where we're going. It's not in the homework yet, but that's a whole thing. That's why we did limits, is because we need this concept. Not so much that we need to know how to work out those problems, but we need to know that we can do it. Question?
Would a tangent line always be a vertical line?
No. It'll be straight line. So this one is not vertical. It could become you'll see what we'll study is that when we're at like a minimum or a maximum, we get a horizontal one. If you do ever get a vertical tangent line, that means you've gotten to a point of where it's undefined. That's the definition of tangent line. It goes through the function at 1 point.
But it's not like a function like the vertical line. That's the one. That's the way it goes through points. Right?
That's just to determine if it's a function or not. But this is a little different. So this is just the tangent line. And what we're going to see is that the slope of the tangent line is what we call the derivative. It's the instantaneous rate of change. So if you're driving a car, it's the speed you're going right now. It's not I measure this and then I measure this and I get my average rate of change and I tell the cop, oh, it's only going 55 miles an hour on average. Well, radar got you going 210 miles in that 2-second period. So, hey, that's what you're getting billed for, So instantaneous rate of change. So this is a very powerful tool for us, right? Or will become one. So far, hopefully you're getting through all of this, but what I want you to see is the bigger picture is what limits are is as we get close to it, we've got this experience that, it makes sense that if I come from the left and the right and it's going to the same value, that's what it should be, because that's what we need. If you were in church right now, we would be talking about faith. In a math class, you need faith that a derivative actually exists, because it doesn't, right? When we try to show a slope of a tangent line, you can't get slope if you've only got 1 point. But if you believe in limits and you have faith, it'll work. And it'll get and the good thing about things is a lot of times with math it was that way. It was sort of these intuitive things and people, they were burned at the stake, Copernicus, what? The planets go around the sun? You crazy? A lot of scientists have been thrown into jail or whatever because people didn't believe them, but they were right. And that's the kind of thing is our math isn't always intuitive, but in this case, we can use limits, and we're going to get to that derivative. And that's what we'll spend the rest of this class on talking about. At this instant, I can see where we're going, and that's calculus. Questions? All right. Anyone want to stay after, just let me know, and I'll be here.
I need help.
Okay.
I can't get it on my computer right now, but I don't know if you can pull up the homework or not. On questions 11 and 13 for 10.3.
Okay. Yeah.